Okay, the topics today. Topics. First, I want to compare Newton's method and the secant method. Compare Newton and secant method. And the second topic, section 4. Section 4 is a summary section. Now we have Newton, secant, bisection, Stephenson, right? Big summary. A functional iteration and physics point. Before I present these two topics, let me finish in the last class, I want to find the convergence rate for secant method. Yeah, let me finish that topic. Yeah. This formula is secant iteration. K start with 1. Secant method. How fast? I want to give the convergence rate, but we need some assumption. But the first one is we assume xk approaches some root of the equation. This equation f of x is still this equation. R is a root of this equation. Second assumption is derivative at R non-zero. Second derivative also non-zero. And the third assumption, xk plus 1 minus R absolute value over xk minus R alpha is approach some number 8, where alpha greater than 1. Yeah. Now, I want to determine alpha. In the last class, I have obtained this limit. Which limit? Yeah, this limit. K approaches infinity. Ek plus 1. Ek plus 1. Ek is xk minus R. Yeah. Ek plus 1 over Ek minus 1. Ek approach 1/2 f second derivative at R over first derivative at R. Let me denote this by C. So from this limit, we have when K very large, yeah, this location is simple, means much larger than 0. So when k very large, then we have ek plus 1, k minus 1, ek. Roughly is equal to c. Now from here, we have ek plus 1 roughly is c times ek minus 1 times. On the other hand, from this assumption, when k is very, very large, sk plus 1 minus r, it is an ek plus 1. Yeah, absolute value over ek absolute value alpha roughly is 8. Okay. Now from here we have ek plus 1 roughly is 8 times ek alpha. Now I attacking this approximation here. So this is let me see. Take absolute value on both sides. Absolute value. Yeah. Absolute value. Let me see. Left side is A times ek alpha left hand side. How about right hand side? Right hand side. Here. Move A to the left side. So A inverse ek plus 1. Move A to the left side, and then the power, okay, apply 1 over alpha. The power, okay, we get roughly is ek. Yeah. Move A to left side, then take 1 over alpha, take power. Now here, plug in the approximation here. So ek minus 1 roughly is A inverse ek, then 1 over alpha, right? Times ek. Yeah. Okay. Move constants to the left, ek to the right. Let me see. Constant to the left, then I get what? I get 1 over alpha applied to the 2 factors. And then move this A to the left side. Then I get A1 plus 1 over alpha. Right? 1 over alpha times negative 1 over alpha. Move it to left side. How about C? C, move C to the left side. So C inverse. Yeah. So roughly is ek to right side. Ek to right side, then again ek. 1 over alpha here. So 1 over alpha plus this ek plus 1, right? And also this ek to the right side, so minus alpha. Yeah. Right. Okay, now from here we have about this approximation when k is very large, left side, right side, almost the same, okay? But left side, constant. Can you see that? Alpha, constant, A constant, C constant. But right hand side approaches 0, 1, because we assume the error approaches 0. Then how to keep left side, right side about the same? The only answer is the power 0. Right? From here, we get 1 over alpha plus 1 minus must be 0. Otherwise, left side, right side cannot be the same. This is if I multiply alpha to the both sides, then I have a quadratic equation about alpha. Multiply alpha. Okay. And now the root by quadratic formula. By quadratic formula, the root I get alpha is 1 plus square root of 5 over 2. So roughly 1.62. It turns out that in this assumption, the alpha is 1.62. Newton's method here is 2. So Newton's method faster than secant method. But secant method still when alpha is 1, we call the convergence linear. Alpha greater than 1, still linear. So secant method still linear. But slower than Newton. Now, this is I finished this topic. I didn't finish in the last class. The convergence rate of secant is 1.6. Now, next, today, I want to compare Newton's method and secant's method. And I want to look which one is better. Which one? Okay. Let me erase. Topic 1 today. Compare secant method, secant iteration or secant method, secant and Newton iteration, Newton's iterations. Yeah, let me write down the formulas. Newton, okay. Newton. The formula is this. K 0, 1, 2. Yeah. How fast? So fast. E K plus 1 square when K approaches infinity is some non-zero number greater than C. Yeah. infinity. Very fast. Order 2 method. So this limit says that when k very, very large. Yeah. This limit says that error ek over ek plus 1 square roughly is c. ek move the bottom to the right side roughly c times ek plus 1. No, the top is k plus 1. Right? K plus 1. Bottom is k. Okay. No. This is k plus 1. K plus 1. Bottom is k. K plus 1. Then k squared. Yeah. When k is very large. Don't forget the error is going to 0. Previous step, the error is ek. Now, ek plus 1, the error is square of the error of previous step. If the previous step is, say, 10 to negative 2, then this is a 10 to negative 4. 10 to negative 3, 10 to negative 6. Very fast. So this is the order 2 method. Yeah, order 2 method. All right, now, secant. The formula for secant, let me erase. Okay. Erase. Secant method. Formula. To run this secant method, we need two initial guesses about the root R. So k start with 1, okay, 2, and so on. We just put that convergence rate is 1.62. No, it's this. Okay. K infinity ek plus 1. This is a ek 1.62. Okay, is c. Okay, this is a different c. How about this is a cs secant? This is a cn Newton. Different. The c s within the c. Also very fast. Now let me compare. First, Newton is a computational method in theory. Okay, is a method in theory, not in practice. Okay. Not in practice. Why? Because this method requires derivative on x. In practice, we don't have formula about the function x. We don't know formula. Usually, no formula, okay, for x. No formula for x. There's no formula for x. How we know the function at xk? Yeah. At xk minus 1. How? do experiments to obtain data. Okay. Right? You are from engineering, you should know that, right? Do experiments, okay? Yeah, obtain function value and xk and xk minus 1. We don't have formula for xk. Not derivative of f. How we know derivative of f? No way we can know derivative of f. So this is a theoretical method, not technical method. First, this is a technical. Okay? Second, number two. Yeah, number two. I want to compare the computational cost. Each step, each step of Newton. How many function evaluations we need to perform? Each step of Newton method. How many function values we need to know compute? Two, right? We need to compute x function and xk and function derivative and xk by two, right? Two, right? Two function evaluation. And how about secant? Each step of secant. How many function values? How many function values we need to perform? Secant. Three. This is the same. How many we need to perform? So let me explain. When k is one, when k is one, when k is one, we need to load f x0, right? F and 1, right? Yeah, this is k is 1. K is 2. We need k is 2 in order to obtain x3. Then we need k is 2. We need f x1 right here, and then f x2, right? Yeah, right. K is 2. K is 2. To get x2 plus 1, x3, we need this 2, right? K is 3. K is 3. To get x4, we need what? What we need? F x k is f x2 and f x3. Okay, but this x1 already computed here. See, this x2 here we already get x2 from the previous step. So actually, each step of secant method, how many function evaluations we need to perform? Just one. Yeah, just this one. Makes sense, right? Hey, now from the point of view of computational cost, two steps of secant method in computational cost is the same with one step internet computing. Two step secant method computational cost is the same with one step internet. Now I can combine two steps of secant method. Okay, yeah. Okay. Now I combine. Oh, okay. Now here. K is 1. K is 1. I get X total. I get X total. Okay. Then K is 2. I get X3. K is 3. I get X4. Okay. Now I combine these two. So X2, X4, then X6, X6, X8. Okay. Yeah. Combine these two together as one iteration. Okay. Now, when I combine, what is the new rate of convergence? Yeah, one step is 1.64. Yeah. Combine two. Okay. So, okay. Now, from here, when K is very large, we have, yeah, from here we have EK plus 1. Absolute value roughly is CS, CK member, EK 1.62. Yeah. Right. Now, how about EK plus 2? EK plus 2 roughly is CS EK plus 1. 1.62. Right? Okay. Now I'm plugging this approximation here. Then I get CS CS. Because all the factors are positive, so I don't need absolute value. K 1.62. 1.62. Okay. All right. Now here is equal to CS. Yeah. Apply 1.62 here. Yeah. Here. Apply 1.62 here, and then 1.62 here. Okay. So this is a 2.62 because there is a CS in the front. So here is a 1.62 x squared. What is that? 1.62. 2.62. 2.62. Yeah. 1.62 x squared. So if you combine two steps of CK method, computational cost is the same with Newton method. And also Newton method law a practical method. If I combine two steps of CK method, then I get the convergence rate is better than Newton. Newton just order 2. This is the order 2.6. So which method is better? Of course, CK method. So in practice, no one use Newton method. CK method. But of course, the advantage of Newton method is it can be extended to solve 6 terms of equations, but CK cannot. This is the drawback about C. Okay, makes sense, right? Okay. Now, topic 2. Topic 2, section 3-4. A summary section. Okay. Let's make a summary. Okay. Yeah. Yeah. CK method, actually, all the convergence rate, all the 2.6, super fast, very, very fast. Solve an equation if your initial guess initial guesses are close to the root that you want to find, then you will see just a few iterations get the answer. Okay, now and 3, 4 section. Three, four. Functional iteration. Iterations. Okay. Functional iterations are still solve a single equation, not about system of equations. Single equation. Now let me introduce definitions, some definitions. Number one, iteration of the form. Of the form. Which form? Yeah, this form. Sk plus 1 is capital F, some function. Yeah, capital F different from little f. Capital F, some function. It's called functional iteration. An iteration of this form is called a functional iteration. Say, for example, Newton iteration is a function iteration. Yeah. Good. Yeah. Say, for example, Newton. Yeah, Newton. Newton iteration. What is Newton iteration? Yeah, here. Xk plus 1. Xk minus f xk derivative xk. This is a functional iteration. Why? What is the capital F? Capital F. This is a capital F. Capital F is x minus f x. Yeah, this function. So any result about a functional iteration can be applied to Newton because Newton just a special case. Stephenson method. Stephenson iteration is a function iteration. Yeah, Stephenson. Iteration. What's Stephenson iteration? I mentioned this method before. F xk squared over f xk minus f xk. Yeah. You can find this method in I don't forget the section number. Okay, in previous section. Functional iteration. What is the corresponding capital F? Yeah, capital F. Yeah, capital F is an x minus f of x squared, then over f x plus yeah minus f. How about secant? Secant is not functional iteration. Secant. No, I don't think so. Yeah. Secant is not. Secant. Secant. The iteration is this. xk minus f xk minus xk minus 1 over f xk minus f xk minus 1. This is not a function iteration. Why? Because the right side involves not just xk, but also xk minus 1. Not function. Yeah, this is the definition about function iteration. Iteration of this form. Function. Definition 1, definition 2. I erase. Okay. The first part, number 2. If capital F and X as some number, function F at S is equal to X. We call as a fixed point of capital F. Definition number 3. Number 3. A function is said to be contracted on a set, say, J, capital S, okay, set, okay, the first letter of the word, S-E-T, set. A function is said to be contractive if we can find some number lambda, yeah, between 0 and 1, such that capital F and X minus capital F and Y absolute value less than or equal to lambda times contract. Function value. The difference in function value is less than or equal to lambda less than 1. Yeah. Yeah. Okay. Now, one theorem about contracting capital F is one. Yeah. Theorem. I don't present the proof. Okay? Just present the proof. Okay. Let S be the whole subset of the real line closed subset say closed interval. Yeah, closed interval. This is a closed subset. Open interval is not a closed subset. Let S be a closed subset. Okay. If capital M is contracted, yeah, contracted of S into S. What this means? S into S. Yeah. Capital S is function value always in S. Okay. X from X function value also in X. Yeah. X from X compute function value at X. The function value in X. Yeah. In other words, capital F maps X into X. That's it. And also contract. Yeah, second part. Now conclusion. Maybe okay. Okay. Everybody knows sine is function, right? Sine is a function of sine is of left infinity to infinity into negative one. From this set, any number, sine of the number always between negative one. Sine is a function of from this interval into this. Now conclusion. Then, okay. Then, number one, hey, it can be solved. This F has unique one and only one. Basic point little s in capital X. Little x, a number. Okay. It can be solved. A B starting with any point in X. Functional iteration converts to the physical point. Okay. The sequence. Which sequence? Yeah, this sequence. K is 0, 1, 2. This sequence converges to the base point little x. Any example? Say, take a look at this example. Yeah. Take a look at this. Example. Consider the following iteration. Initially, it is negative 15. Then iteration minus 1 over 2. Absolutely. Okay. This is a iteration entry. It is a functional iteration. Why? Because I can write the right side as where f of x is 3 minus 1 half. Absolutely. This is a function iteration. Right? It happens that is capital M contracted. Yeah. Okay. Capital M is contracted. For the details, you can take a look at my notes. Contract from where to where? From negative infinity to positive infinity into infinity. Now, by fill up any starting number, then this will convert to the unique basic point. Yeah. So x converts to guaranteed to have s and xk converts to this. Then how to find x? Easy. How to find x? Easy. Here. Let k approaches infinity. Then this will approach s. And this will approach s. Now solve this equation. Solve this equation. Solve s 3 minus 1 half after the measure of k. Solve this equation. Then we get the number is 2. Yeah. S then s. For detail, you know, so the sequence will convert to 2. No matter, actually here, the starting point is negative 15. Any number, start with any number, is iteration converge to 2. Okay, see you Monday. Monday, I will present convergence of the rate of convergence about iteration, about functional iteration. Convergence rate. We always talk about convergence rate to compare which member is fast, which member